Hello, my name is Michael Whitner, and I will teaching you about Windows anti-debugging techniques through the lens of implementing them. So, a little bit of background about this presentation. I wanted to implement CTF challenges that included Windows anti-debugging techniques, so that way participants can actually get a hands-on feel about how to reverse engineer hardened Windows binaries. Many CTFs focus their time on Unix, so I want to make something a little bit different. So, with this, for the scope of this presentation, I will be talking about three anti-debugging techniques and two that I analyze but will implement in the future use. So the first check that I did for debugging was through heap flags. So with this technique, I checked two sets of flags: the heap flags and the heap force flags. If these are set to anything that they're not supposed to, then the program exits. So the two, so for the heap flag, it has to be. It's most of the time set to heap global when running the program. And for the force flags, it's usually set to nothing. Um, so if these two are modified to be something else, it's more than likely that a debugger is being attached to them, because debuggers have the tendency to modify those flags. So a little bit on the code that I implemented. Um, the first two helper functions that I created were just mainly getting the offsets to where the flags were located. As you can see with the heap flag, there is a 64-bit offset and a 32-bit offset. This is important because if you have these wrong, then you're grabbing the wrong data. Um, when I'm actually checking the heap itself, I have to retrieve the process environment block and the 64-bit process environment block, um, and then I first and this is how and this is where you could check the heap flags through the process environment block. I then take the offset and check and add add the offset to the process environment block, and that value will then be where the heap flag and the heap force flags will be located. And that is through this code here. I then do a check. I then do a check to see whether the heap flags is set to anything but heap global, or the force flags are set to anything that is not zero. If um, otherwise, I exit. I then repeat the step for the 64-bit process environment block, um, and if that returns false, then I exit. So a way to bypass this is by actually simply overriding the value itself. You can do this through the debugger, some PowerShell, or even plugins like Skylahide. So if you set the two flags to what they're supposed to be, then you won't have an issue. And you can even in some cases, you can just use a different debugger and you'll bypass it. This happened in the case for me when I used um, x64 debug instead of WinDebug. The next anti-debugging technique I checked was through checking if instructions were injected um, into the function call through a checksum. So with this, the checksum can verify whether a function has been modified based on the fact based on calculating based on the fact that there are um, instructions being inserted like int3 or whatever the debugger wants to put in. If the original checksum and the recently calculated checksum don't match, then that means a debugger is likely being used or it's being tampered with. So how I did this was I took the address of where so I took the address of where I wanted to check. So in this case, begin simulation, and I check, and then the address of end simulation. So subtracting, if I take the rate, if I calculate the checksum between those two addresses, I could see whether the code in begin simulation has breakpoints inserted. And I use this calc func CRC to generate my checksum. If the checksum that I just calculated and the value of the original checksum don't match, then it's likely being tampered with. For the bypass, there's no universal way of bypassing it. You can do this by modifying the output of the checks of the original checksum value. You can modify the output of the function, or in some cases you can patch it. But it's very much so implementation dependent. The final anti-debugging implementation I did was through hardware breakpoint check. Was a hardware breakpoint check. What I did was I took advantage of Windows API's context debug registers to see whether they were set. And particularly, I retrieved the context from the current thread and determined whether the debug registers that are used for hardware breakpoints, particularly 0 through 3, whether they are set to anything but 0. If they are set to anything but 0, then that means that there's a debugger likely being attached. So a bypass to this, other than patching, is something that I researched through learning more about what Git thread context does. So Git thread context calls anti-git context thread, which is a low level API, and particularly it's implemented through anti-dll.dll. This also has functions like anti-set context thread. So what I realized was, after retrieving the thread and getting the context debug registers, I can reset all of the values of the debug registers to 0 through anti-set context thread. This means that we can bypass the check, and it makes it seem like hardware breakpoints are not even being used. Here is an example of such an implementation. This I found through a blog post. So this is which I found kind of fascinating how they did it. They hooked onto the threads, and they also retrieved NTDLL and aligned the process. So essentially, this is used to call NT-get context thread. This is used to call NT-set context thread, and then this hook thread context actually retrieves the process address and allocates the memory and puts it in where it's supposed to be. So that is essentially how this works. So some other considerations that I'm thinking about are handle tracing and debug messages in order to catch software breakpoints. Through this, they're both taking advantage of Windows exception, but through different ways. For handle tracing, it's checking close handle to see whether it's actually throwing an exception. it's actually throwing an exception, or if it's throwing false. In trace mode, close handle will actually throw an exception, while in non-trace mode, um, which is in non-trace mode, that means there is probably no debugger being used. Um, that means um, it'll return false. Um, so through this code, um, I so you have to put initially push onto the stack the function you want to use to check whether an exception is being used, um, and then you call close handle. If it's throwing an exception, meaning it's in trace mode and the debugger is being used, then you exit. Otherwise, you have this assembly code here to reset to what you were originally supposed to do and go back to your original code. Um, with debug messages, it's almost like an inverse try except block. Um, so in the try block, you want so with the debug messages, it's specific to Windows 10. So if you're in Windows 10 and you raise an exception, it prints immediately to the debugger. So with this, you want to raise an exception. You want to try to raise an exception. If it's successful, then there's a debugger being present. If it's not able to print to the screen, that means a debugger is not detected. This method does not necessarily work with lower lower versions of Windows, like 7 or XP. So if you want to learn more, I have put into the link 3 blogs, the 3 sources I've used in order to implement this and learn a lot about this. Anton Kukulov's blog, it is where I learned how to implement the techniques, and you've seen some of his code, particularly the hardware breakpoint hooks. Um, Cody Cutler and Anton Burtsev's PowerPoint slides and Peter Ferry's anti-debugging reference helped me learn what they actually do further and actually learn how to reverse engineer it. And if you want to link to the slides so that way you can get the links to this, this is the link. You can go to this link to come to my slides. And thank you for listening to my presentation. I hope this was useful and you've learned a lot. Feel free to reach out to me if you have any questions.